All right, exponential functions. I just wanted to go over a few things with you again, introduce something. Hopefully I'll have time now that I've just rambled on for 10 minutes. That's kind of important. And then, guys, I didn't create a new homework for tonight. We'll get back at it tomorrow. So just finish up the first 2 days' homeworks if you have anything left, and we'll get back at the homeworks tomorrow. All right, here we go. Exponential functions, right? Exponential growth, exponential decay. We saw the graphs and how they behave yesterday. Depends on what the base is. The base is always a positive number, but if the base is a number bigger than 1, it shows growth. If the number is a fraction between 0 and 1, it shows exponential decay. So let's just highlight a few important properties. Now, this applies to the parent functions, the simplest versions of exponentials. This is pre-transformation information. All of this applies to exponential functions that have not been transformed yet. All right, so they all start with a horizontal asymptote at the x-axis, the line y equals 0. In their original pre-transformation form, all exponential functions contain the points -1, 1 over a, 1 over the base. They contain the y-intercept 0, 1, and they contain the point 1, a. When 1 goes in, the base comes out. Now, whenever I'm graphing on the online homework, 0, 1 is always the point I click on first because it's on every exponential function before you transform it. So it's always like my start point when I'm trying to create those online graphs. All right, and then again, the graph will show exponential growth when a is bigger than 1, and it will show exponential decay when a is a fraction between 0 and 1. Perfect. Okay, so here is our exponential growth. As x gets bigger, y gets rapidly bigger at an exponential rate. When on exponential decay, when x gets bigger, y gets smaller at an exponential rate. But notice, negative numbers and 0 do not live on this graph, right? Or as the y-coordinate, I should say. So 0 and negative numbers do not come out of an exponential function. So when we work with the inverse, a logarithm, since those outputs become the input to a logarithm, you will not be allowed to plug a 0 or a negative number into a log. You will not be able to take the log of a negative number or 0 because they don't come out of an exponential. All right. I'm going to go over one more graph, and then I'm going to get to the number E. Very, very important. All right, so guys, I wanted to go over this just in case anybody was struggling on the homework. Maybe the homework was super easy, and that's even better. But just here's another example. If they ask you to sketch the graph of f of x equals 2 minus 4 to the x plus 3, clearly this is an exponential function. The variable is part of the exponent. So the first thing I like to do, I don't like the way they wrote this. I don't like this 2 that is not attached to the base to be in front. So I always rewrite it as f of x equals -4 to the x plus 3, and then I put the plus 2 at the end. Because I feel like transformation-wise, that makes more sense to me. That plus 2 is on the outside at the end of the function. So I can definitely see that it happens to the y's and not the x's that live on the inside. And then again, this -1, he's not your base because the x plus 3 is only on the 4. If I wanted the x plus 3 to be on the 4 on the negative sign, they would have had to use parentheses. And remember, the base of an exponential function is not negative. So really, this is like -1 times 4 to the x plus 3 and then plus 2. So I can really start seeing all of these transformations that are going to take place. All right, well, first of all, let's recognize the parent. Who's the simplest version of this exponential function? If you take all of that, transformation changes to the equation away, you're just left with f of x equals 4 to the x, which is a exponential function that will show exponential growth because it has a base that is bigger than 1. All right, let's get some original points and some original information about this function. What points lived on the original function? Well, guys, the 3 easiest points to create are when you plug in -1, 0, and 1. So if I plug in -1, 4 to the -1 is 1/4, 1 over 4. I plug in 0, 4 to the 0 is 1, so 0, 1 was on the original graph. 1 goes in, 4 to the first power is 4, so 4 is on the original graph. And then, guys, if you want more points to transform, just keep plugging in x's. Plug in 2, plug in -2. Keep making points so you have more points to transform if the transforming is confusing you. All right, here we go. Now let's figure out also, remember, every exponential function starts with an HA at y equals 0. They all start with a domain of all real numbers, and they all start with a range from 0 to infinity. All right, let's make the changes. So this -1 is on the outside of the function. So that's going to cause us to times the y values by a -1, which two things happen. It causes an x-axis reflection because all of the y coordinates are changing opposite signs, and it's causing it to stretch by a factor of 1. So the stretch isn't really there, but the x-axis reflection is. So this will be -1 times the y values. So picture this graph is being reflected over the x-axis. So it's being reflected over the x-axis. So you can see if the graph looks correct. All right. This +3 up here, that's happening to the x's. So it has the opposite effect. That's going to cause a horizontal shift to the left 3 units. We're going to take the x's and we're going to -3 from them, right? It's going to cause the whole graph to shift left 3. And then this +2 is on the outside of the function. So that's being added to the y's, and it's going to cause the whole graph to shift up 2 units. All right, let's do it. Let's make these changes. Let's get our new points. All right, so take -1, times them by -1, because -1's an x. Take -1 and -3 from it. That's what we do to our x's. So -1 minus 3, that moves it to -4. So now he's sitting at -4. Okay. All right. Take the y coordinate 1/4, times it by -1. So now it's -1/4. And now add 2 to it. -1/4 plus 2 is positive 1.75. All right. 0, 1. Take 0, -3 from it. He moves to -3. Take your y coordinate 1, times it by -1, which is -1, and then add 2, and you get 1. All right. Take your next point, 1, -3 from it. So now he's going to be sitting at -2. Take 4, times it by -1. So it's -4, add 2, and now it's -2. All right, your horizontal asymptote, guys. It was sitting at the x-axis y equals 0, but think about it. If it's the line y equals 0, if you move your y's up or down, that's going to affect it. If I take the 0 and times it by -1, that doesn't change it. But if I take the 0 and add 2 to it, it's going to bump that HA up 2 units. So now it's sitting at y equals 2. Your domain, nothing's going to change your domain. The domain of an exponential function is all real numbers. But your range, guys, it used to be going towards the HA at 0. But now the HA is at 2. So now your graph is going to go from 2 to infinity because your HA shifted. All right, let's plot it and see our graph. -4, 1.75. -3, 1. -2, -2. And we have an HA at the line y equals 2. So guys, remember, this graph has been reflected over the x-axis, vertically stretched by a factor of 1, so not really stretched, and then shifted to the left 3. So now it's going to go through these 3 dots. It's going to hug that asymptote, and then it's going to get exponentially smaller. And there is your transformed graph. Okay? Everybody okay with that? Again, technically online is easier because all you have to do is put these transformations into your little transformation box and it makes all of the changes for you. Okay? All right, let's do one other thing now. The only other thing I want to accomplish today is I want to introduce a number to you. You've probably seen it maybe in a physics class or even last year in Algebra 2 when you were working with logs and exponential functions, but it's a really, really important number and you have to get used to who he is and how we're going to use it. So guys, I want to define the number e. So it's kind of like, wait a minute, did she just say the number e? I did. E is a number. It is not a variable. He's like pi's cousin, all right? Pi is an irrational number. So is E. E is an irrational number, and he plays a huge role in these exponential growth problems, these population, these compound interest, these money problems. So you have to know who he is. So I want you guys to take a look at this expression. It's an exponential expression because the unknown is part of the exponent. It's the expression 1 plus 1 over n to the power of n. So back in the late 1600s, early 1700s, there were 3 mathematicians, Bernoulli, I'm never going to say these names right, Euler, and Napier. They were working, guys, back in the day, they didn't have calculators. So it would take them years to like figure out math problems just to solve one math problem. So it believed that this guy Bernoulli was working with a compound interest problem, couldn't solve it. So then years later, Euler started working on it and he solved it. So Euler got the credit because his name started with an E and he got to name this number that they ended up discovering together because technically working with it later, he was the one that discovered the number E. So it's named after the Leonard Euler guy, the guy that they're saying found it. But anyway, they were working with a compound interest problem and they discovered a pattern. The compound interest formula is extremely similar to this expression. So when they were working with a compound interest problem and they came across this expression, watch what they discovered. When they started plugging values in for n, they were expecting the value of this expression to get bigger and bigger and bigger. But it didn't. Something happened when they started working with this expression and n got bigger and bigger and bigger. Now, normally I would have you guys fill this chart in, but just because to save time, I'll let you know. So when they let n be 10, they found out that the expression equaled this, 2.59374,246, and then it just kept on going. Okay, well then they're like, all right, well what happens when n is 100? So then they plugged 100 in, 1 plus 1 over 100 to the power of 100. Then the number became this, 2.704813,829, and so on. So the difference between 10 and 100 is huge, but the number itself barely changed. So then they said, what happens when it's 1,000? So 2.7169, sorry, I'm trying to copy this down, 23932, and so on. So again, when you go from 10 to 1,000, that's a big jump in the number, but the expression is not making these gigantic leaps and getting any bigger. It's actually not getting much bigger at all. It looks like it's heading towards a fixed value. So then they plugged in 10,000 and they got 2.718145927, and then it kept on going. So they're realizing that as n gets bigger, the value of this expression is converging and slowly but surely heading towards becoming a fixed value. So I'm just going to jump right to it just to save time. When they plugged in 10 million, so 10 million is a lot bigger than 10. The answer became 2.718281693, blah, blah, blah. So they realized that as n gets bigger and bigger and bigger, as n goes to infinity, if you will, the value of this expression doesn't get bigger, well, much bigger. It's heading towards a fixed number. And the number that they said it is heading towards is E. They let the limit of this expression equal the number E. They named this number that it is heading towards becoming the number E. And guys, it's wild. If you Google the number E and like his applications, he appears all over the world in physics, in math, in there are flowers that like petals will like form at a rate of E. It's crazy when you see how many times this number E pops up in just the natural world. So he became known as the natural number, actually. All right, and that's why we got the natural log when he is the base. But either way, so we are going to call the number E. E is equal to the limit of 1 plus 1 over n to the power of n as n goes to infinity. As n gets bigger and bigger and bigger, the limit of this expression, the number he is heading towards equaling, is E, which is approximately 2.71828, blah, 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 blah. So again, he's a number, but he's a fixed number. He's an irrational number. He is a decimal that never ends and never repeats. So in the future, number one, I never want you looking at E in a problem like he's a variable, because he's not. He's a number. He's a value that we know. Also, I don't want you saying, and someone says, hey, do you know who E is? And you guys say, yeah, he's 2.718. No, he's not. The answer to the question, who is E? He is the limit of this expression as n goes to infinity. So anybody who tries telling you, oh yeah, he's 2.78, no, he's approximately that, but he is defined to be the limit of this expression. All right, and we're going to use him in all kinds of exponential growth and decay problems. So again, that's who he is. He's approximately the number 2.71828, blah, 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 but he is the limit of this expression. He is the number that this expression is heading towards becoming as n gets bigger and bigger and bigger. Okay. All right. So I'm going to stop there. So we know who E is. Now we'll be able to use him in our exponentials as a base. We'll see him pop up a lot when we get to the logs in the next section. He has a lot to do with population and things that are growing at a continuous and constant rate. Okay. All right.